And so then people say the solution should be the government is going to basically mandate information security. But even what happens is that today, as we know, the government is owned by the lobbyist. But if you push hard enough, the government will make enact regulation, but that needs to be enough pressure. So that's basically my background statement. And then the answer that I gave is that the deployment of cryptography is often a reactive action and not proactive. And this is due to an acceptable high level of hacking or due to regulations. It's not just something that people do just in order to be more secure, it is for economic reasons. And well-known examples are the use of encryption by the petrol industry for geological data after it became clear competition might have been eavesdropping on it and basically saved a lot of money because geological exploration is quite expensive. And this is from the Hellman's paper. The deployment of SSH around 2000 when too many telnet sessions were being sniffed. The requirement by credit card companies to use SSL for e-commerce. And the introduction of pin and chip in the UK when credit card fraud became too big. So that's all reactive. Are there cases where we can clearly show that people should have been thinking proactively? I think so. And so what I would like to add to that is that those that do not take information security into account should realize that they could burn their fingers. And there's a nice example that basically come to mind. And this is a potential example. I'm not saying that this is the real story. And that's AIS. Now, most of you who basically are familiar with crypto, you know AES. That's a block cipher. No, this is AIS. What is AIS? It basically allows you to find the position of ships. And so this is a web page called AIS Live. And what you see in there is that you can actually do a request for a 2-week free trial. Okay? And what does it give you? And this is actually from a different web page. It gives you live tracking of the ship locations. In particularly, when you look around Somalia, you can actually see where the ships are located. And so the Sunday Times, which is a British newspaper, November 23rd, 2008, made the following statement. It's also shockingly simple for anyone to track vessels online or to tune into ships' AIS beacons. So automatic identification system, that's what AIS stands for. They transmit a ship's exact position, size, and cargo. So if the Sunday Times is correct, the cost of lack of privacy in this technology is in ransoms alone estimated at 40 million. That was at that time, so it may have even increased. So what you clearly see is that the people who designed it completely ignored the information security aspects of it, completely ignored all the basic things as the need to know. I mean, why the heck do I need to know where all the ships are in the world? Okay? And then not only that, I can get a free trial for 2 weeks. Okay? So it's clearly, you should think proactively. Unfortunately, often it's not on, and here is yet another example. So, is Odlyzko correct when pointing out that no major disaster has happened due to lack of information security systems? My reply that I usually like to give, and also to Ros Anderson, who says, forget about critical infrastructure protection, that attack, it will never be attacked, is that we had no major meteor hit Earth since the discovery of computers. The last one was in 1908 in Siberia. So I'm talking about electronic computers. So, but we know we will get one, okay? And so the way that these catastrophes are analyzed by people trying to analyze them is that they have a high impact. So the cost is quite high, but the probability is very low. And those of you who remember your calculus, if you have two functions, one tending to 0, which is the probability, and the cost tending to infinity, and you multiply them, what's the answer? Oops, it depends on the functions. It's quite interesting because what happens is you have functions that we actually don't know what they are because they're events that occur very, 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 very rarely. So even trying to make a model for them, we're going to be off, okay? And then looking at this impact that they may have, since we don't know how big these things will be, how frequently, etc., etc., in particular, since we don't know how big it will be, we don't know how the cost will be. So we have no clue on actually estimating what this will do. And so, since it hasn't happened in the last 60 years, does not mean that it will never happen. So, but maybe I also should be critical about myself. Maybe I have been a neo-Luddite when stating in 1983 that what, at that time, the concept DCS, the acronym didn't exist. what I was looking at is basically an oil refinery, and I pointed out in 1983 that you can actually hack that by having access to the local area network, which when Honeywell came out, Honeywell Control came out with using Ethernet cable to actually control the computers and communicate with the computers on such an oil refinery. And an oil refinery are several square miles. What happens is that on this oil refinery, you will find public roads. You just can travel through, and you will actually see sometimes these cables. And so at that time, even though there was no internet, you could actually hack this in, and you could actually send incorrect control statements. And basically, I made the claim that you might blow up such a plant without the need for explosives. Never happened. Never happened. So yeah, maybe I was also screaming and saying, careful with all this technology. But in the meanwhile, although there's never been a major disaster, Vitek Boden, who some of you may have heard about it, hacked a computerized sewage system in Queensland, Australia, showing the potential danger that actually could be done. So that's enough about do we need cryptography. So I think that by talking about basically credit cards, chip and pin, etc., that I hope that you're motivated, that it's actually useful. So what are the strengths of our modern research? And that's what basically, looking at the research in the future is going to be the main aspect of my talk. And so that's why I think we should look at what we have today. I think that proven security is a major success. It can be viewed, I think, as the biggest scientific success in cryptography. It was introduced by Shannon in 1949. And so I disagree with Jack Stern, who at Eurocrypt said that it was introduced by Rabin in 1979. And if you look at Shannon's paper, it has a definition of basically privacy. It says that the ciphertext should be independent. The probability of the ciphertext should be independent of the one of the message pair. And that is a definition. Okay? It's a very simple definition. It's not a long definition as we see today in most crypto papers. It's a very simple one. And there is actually a proof. So there is actually a theorem and a proof that the one-time path satisfies this definition. Adding the computational complexity, that was done by Rabin in 1979. And there he actually has a proof, but he doesn't have a proper definition. And so the paper was rejected, as we all know. And so basically the lesson is that if you're a student and you're writing a paper and your paper got rejected, don't necessarily panic. I mean, Rabin's paper has been cited many, many, many times. It still is a rejected paper, okay? So but one way we could look at it, I mean, we all know who one of the referees was and why it was rejected. But one way we could look at it from a scientific viewpoint is that it didn't have a good model. It doesn't actually define what it wants to do. And so, therefore, by not being very precise and saying what it can protect and not protect, then the chosen text attack broke actually the scheme. And so that's why I think that Goldwasser and Micali played a quite important role by actually putting a definition there. Same as Shannon did, putting a definition. And then they said this very, very narrow definition basically limits the attack to quite narrow, in a quite narrow sense. In that very narrow sense, under an assumption, they then proved that their scheme was secure. The assumption is still unproven, but that's unfortunately the only way that we can proceed today. And I think there have been some successful developments. And I'm going to take some that I played some role in myself actively, key distribution. So what you see in key distribution is that today, the community is able to design, prove and secure the key distribution schemes under some assumption that are actually practical. And similar things have actually been done for encryption. And so if you look at encryption, you can start with Vernam, which basically was unproven. And actually, if you look at, it was not yet called a one-time path. The idea of actually using it only once came afterwards. And that was 1926. Then Shannon in 1949 proved that the one-time path, when actually the one-time path version of the Vernam scheme was actually the secure. Goldwasser and Micali introduced the notion of semantic security and had a proven secure scheme that achieved security, but it was extremely impractical. Nauer and Jung basically had a public key system, crypto system, provably secure against lunchtime chosen ciphertext attack, and we had to wait until 1991, which is not that long compared to 1990, until there was actually, by Rakov and Simon, a scheme that was secure against all known types of social ciphertext attacks. Then what happened is that all these schemes were completely inefficient, and Kramer-Shoup was the first practical public key encryption scheme secure against CCA2. So why do I put quotes around practical? Because when you talk to practical people, they say this is not a practical scheme. They say it still needs so many more exponentiation than in the case of RSA or El-Gamal. They say, and that's why we don't want to use it. So Kramer and Shoup in 2002 formalized hybrid encryption and proposed a class of schemes. And more recently, Kurosawa and myself basically, and this just appeared a few weeks ago in the Journal of Cryptology, together with Gennaro and Shoup, who improved on our scheme, we basically showed that one can make an even more practical version of what was done earlier by Kramer and Shoup. So are we there at the moment? We're actually, yeah, we're getting closer and closer and closer to actually getting to proven secure hybrid encryption, which is practical. So that, I think, is a major success for the research. But I also think that we need to look at the shortcomings of our modern research. There are several problems, and they are from different natures. So I think we need to start looking at the foundations of modern cryptography. Are they fine? I don't think so. And why are they not fine? Because if you look at, so why did I pick the area of basically the encryption, in particular public key encryption, is that once you look from 1982 with the paper from Goldwasser and Micali, we have had quite a number of papers bringing it from a theoretical solution, very limited first. Goldwasser and Micali is very, very limited. And then theoretical solution in the early 90s, and then moving toward a more practical solution. But when you compare that to the research on conventional crypto, this is not happening. There is nobody today who is looking and saying, we are going to lay the foundations in conventional crypto so that in 30 years from now, we will have a block cipher which is kind of practical, maybe twice as slow as what will be designed at that time by heuristics. No, you go to these conferences as FSE, and they were basically all trying to break the scheme that came out just a few months ago or a few years ago, and they're trying to design a new one. That was what public key cryptography research was about in the 80s. Okay? And that has, except you will always find people who are 20 years behind, but that's basically what has stopped in public key cryptography research. But in conventional crypto, they're continuing with that. And so when you then look at hash functions, the situation is even worse, because with the attack from the Wang from China in 2004, it's kind of now, oops, which hash functions are still secure? MD4 went, MD5 went, SHA-1 went, etc. So we can't claim that everything is going well. And what people should start looking at is what assumptions do we have when we look at Boolean functions? Because what happens is we know how to build these things when you're going to use number theory, and then they become so slow and nobody ever sees that in 30 years we will have something which is basically twice as slow as the current block cipher at that time. So it seems that we have to look at Boolean functions. The problem with Boolean functions is we know worst case analysis, but nobody is looking at actually average cases, okay, as factoring in this git log and this type of stuff.